In this video, we're going to just highlight a couple of things about critical points and talk about mean value theorem. Okay, we have the graph of f prime. We're going to list critical points. Remember, critical points are where the derivative is 0 or is undefined. Okay, so we have the derivative. We're looking for where it's 0 or undefined. Well, it's 0 at -2, it's 0 at -1, and it's 0 at 3, and I do not see any spots where it's undefined. So we're just going to list x is -2, x is -1, and x is 3. These are our critical points. Now, in terms of classifying them, here at -2, the derivative changes from positive to negative, so the original function changes from increasing to decreasing, making this a maximum. Here, let's go to 3. The derivative changes from negative to positive, meaning the original function changes from decreasing to increasing, making this a minimum. And finally, at -1, you'll see that the derivative doesn't change signs. It was negative, and then it's negative, so it doesn't change. The function is decreasing and then decreasing some more, so this is neither a maximum nor a minimum. Okay. Now, I didn't ask you to do this, but I just wanted to highlight, if we were going to graph the original function, we do have quite a bit of information. We know that there's a maximum at -2. We know that despite the fact that there is a horizontal tangent at -1, it's neither a minimum or a maximum. And then we have a minimum at 3. So, this is, certainly I could put this graph a lot of different spots, but this is the general shape of it. It's got a maximum at -2, a horizontal tangent at -1, because the slope is 0 there. Negative derivative means the function is decreasing, then not decreasing, then decreasing some more, and then we have a minimum at 3. The mean value theorem. Okay, you can read the definition here. If f of x is continuous on the interval AB and differentiable on the interval AB, and first of all, I think people notice, well, why are these different? Well, we have to be defined at the endpoints. Okay, and to be continuous at the endpoints, we have to be closed circles. But of course, a derivative by definition is a limit. So if the function is only defined at the endpoints but not on the other sides, the derivative doesn't exist at those endpoints. Okay. There exists a C in the interval AB such that f prime of C is equal to f of B minus f of A over B minus A. I think this is best explained by a picture, and I have this picture right here for that reason. Okay. This red line, if you recall from a couple of chapters ago, is called the secant line. Okay. Secant. The secant line simply connects the endpoints and draws a line between them of a curve. Well, this green line is called a tangent line. And I hope you look at those and say, boy, they sure look parallel. Well, they are. They have the same slope. That's the mean value theorem. The mean value theorem says that as long as a function is continuous and differentiable, which this certainly is, it's continuous and differentiable, that somewhere the slope of the secant line, this represents the slope of the secant, right? This is an average rate of change. Somewhere the slope of the secant line will be the same as the slope of the tangent line, which, of course, we get with the derivative. That's all that says. Okay? Now, I put this other example on because a lot of times the AP exam will ask a question like this. It will say, well, we connected 2 points on this curve like that with a secant line. Is there a spot where the derivative is equal to the slope of the secant. So really, does this hold true? Is there a spot where the derivative is equal to the slope of the secant? And the answer is no. The slope, of course, here is just, it's linear, so it's just a constant slope, and here it's a constant positive slope. But it doesn't have to hold true to the mean value theorem because down here, it's not differentiable. Mean value theorem only has to hold true for functions that are continuous and differentiable. And again, we're just trying to get a spot where the slope of the secant line, or the average rate of change, is the same as the derivative. So how a question could be asked about this is, at what value of x does f of x satisfy the mean value theorem? Well, that's really a three-step process. The first step is to get the slope of the secant line, which, of course, on the interval from 1 to 0, we get f of 1 minus f of 0 over 1 minus 0. Well, when we plug 1 in, 1 minus 2 minus 4 plus 1 is negative 4. When we plug 0 in, we get 1, so we have negative 4 minus 1 over 1, so this is negative 5. I'm just going to make a note. This is our average rate, okay, or the secant slope. Well, the next step is finding the derivative. Okay, f prime of x, 3x squared minus 4x minus 4. And the mean value theorem says somewhere the derivative will be equal to that average rate of change. That's it. This is saying somewhere that secant slope will be the same as the derivative. Well, now we really just use any algebra means at our disposal to solve. I'm going to add 5 to both sides. Okay, you could use quadratic formula now, or completing the square or factoring. I'm going to factor because 3x squared, it can only come from a 3x and an x. Multiplied to 1 can just be 1 and 1, and because it was minus 4x, put subtraction there. So the two solutions here, what makes it 0, are 1/3 and 1. Well, remember that the mean value theorem says it has to be an interior point. Well, the interval was from 0 to 1. So that takes this out. This is an endpoint, okay? This is an endpoint, and therefore it doesn't satisfy the mean value theorem. Okay? Whereas 1/3 is an interior point, so that is the point of x that satisfies the mean value theorem.